So today we're going to do open loop microstepping mode with an encoder to verify that the position is where we want it. We are not going to do encoder corrections, and we are not going to do servo mode, but your basic open loop microstepping mode. We're going to use the StepNet panel here connected to a CompuMotor motor, which is a 1.8 degree stepping motor with a 4,000 count per rev encoder, all wired up to the drive. There's a 24 volt power supply, the B&B USB to serial adapter with the Copley serial cable kit. And just to show you, we've got a 2-axis panel and AC powered. There's the StepNet panel again. There's a 2-axis module, there's a rugged module, and there's the micro module, which is smaller than a business card, which is, here's my business card. And we also make a 3-axis module and a 4-axis module. The 3-axis module is a true plus drive with all the fancy feedback features. The 4-axis module is just your basic 24 volt, 48 volt stepper open loop, maybe CAN or EtherCAT, but just basic micro stepping modes. So I looked up the OS12B CompuMotor Parker stepping motor, and you can see both the series and parallel winding can get you speeds. Here's the parallel winding, and then here's the series winding. The parallel winding can go faster. The series winding requires twice as much current, but both can do 600 RPM. It's hard to believe that the series winding can get anywhere near 3,000 RPM or even the parallel winding, but we'll check that out. As you can see, though, the series winding starts dropping off at 1,200 RPM. The current folds back because of the motor's back EMF. And then the parallel winding can go out a lot further before it starts to roll off. So we'll take a look. So here's the series winding. They stick the yellow and blue together to get a series wiring of the coil. This is an 8-wire motor, so they configure it either as series or parallel. This would require twice as much voltage to go fast. The parallel winding requires half as much voltage to go fast, but twice the current, because the coils are wired together in a parallel format. And of course we have the encoder feedback A naught, B naught, Z and Z naught are the index and return. There's a shield that must be connected to earth. There's a +5 and ground to power the feedback device. So we're going to run through the basic setup to see what we got. It's a rotary stepping motor, not a linear. Just because it's a rotary motor connected to a linear stage does not mean it's a linear stepper. It's a rotary stepper. There's a primary incremental encoder on the shaft of the motor. We are not going to run an encoder correction, open loop stepping mode, or servo mode. And we're going to do position mode and use the digital input for pulse and direction. That's typical for stepping motors. And we enter the data for the motor. I've set the microsteps per rev to 4,000 microsteps per rev. This is a 1.8 degree microstepping motor with 200 full steps per rev. So 1 rev of the motor gets 4,000 counts, and I set the microsteps per rev to 4,000, so that 1 microstep equals 1 count. Now you can make the microsteps 10 times bigger if you want, that's fine, but just to keep things simple in my head, I like 1 count to equal 1 microstep. We've also got calculated values for the initial tuning, and then we can put the drive in max speed mode to go a little faster. This is circular versus square limiting on the motor. We've got rated currents and hold currents, run to hold time, and hold to voltage time for less noise. I ran the auto tuning and used the medium values that it recommended, and we'll take a look at the current loop bandwidth that's produced with the auto tuning values. It should be pretty good, maybe about 1 kilohertz, that's fine. But I like to use the CME2 scope to do my own tuning. This says 900 hertz. That's pretty good. And the calculated values can also be seen on the scope. The tuning of the current loop, apply to the current, auto setup checkbox, hit start. And you can see the integral wind up there, so the integral term's a little high. We could get a little bit more proportional gain out of that. There's no overshoot there. But, you know, this is sufficient current loop bandwidth for rotating the current vector. I don't want to overdo it. I just cleaned up the tuning a little bit. I like those values, so I'll save them to flash. And what we're going to do after the current loop is take a look at the trajectory limits. These are values that we've tested. If you have a step and direction generator sending pulses to the drive, you need to clear these limits. So you can clear the limits, and the only thing that slows it down in a controlled manner is an abort decel. So external profile generation, you must clear the limits. I'm going to turn them back on so that I can do some position loop tuning. So for my first attempt at position loop tuning, I used the profile tab. I got a distance of the move. I used the auto setup checkbox, which looks at the profile command, the actual current, and the commanded current. To do my test, I've increased the speed to see if we can hit that which is shown in the speed torque curve. I increased some XL and decel to get my profile to fit. But I'm going 10 revs of the motor at 3,000 RPM. And my actual current in blue is folding back. So if I zoom into this actual current, we have to watch out for where the actual current is less than 0. That is a stall condition. So danger, Will Robinson, we're about to stall. This is during a decel, so maybe we're okay. But if I tweak up the speed a little bit, I may run into some trouble at a higher speed. We seem to have just whistled by the graveyard on that because of the didn't actually hit the speed I was commanding yet. Let's increase the XL and decel. There we go. So we gave a command for velocity. Our actual current during the run was hitting 0. So we're going to have a stall condition. I have the encoder device on the motor so that I can determine following error. And sure enough, I got a following error fault. I'm going to clear that fault and take the speed back down. So with this power supply, it's actually a 26 volt power supply. I still get some limiting here. So it looks like I can make 3,000 RPM pretty repeatably. There's a little bit of a danger zone here as my currents get close or below 0. While I'm making the move, you're always voltage limited with a stepper, because as soon as the back EMF equals the power supply voltage, you start to fold back. And even if I went to 300 RPM, I come in and out of voltage limit warning. You know, there's not 24 volts at the output. It's a PWM amplifier, so 95% of the power supply voltage, a little IR drop. It all adds up. If you ran this with 48 volts, you'd probably be in much better shape. Even the speed torque curve rating of 600 RPM, I do fold back my current a little bit to about 1 amp, so that limits the torque. You could see a constant voltage limit warning. And again, it's just a fact of the motor, and a fact of the power supply, and a fact of the drive. You know, this is a servo drive rotating the current vector to try to control the motor. We do control the current very precisely. It's not like a cheap chipset that's just slamming the voltage, so the ringing and the current is all under control. So I have a little time here, so I'll show you what the encoder corrections does for us. So I turn the encoder corrections on, and I have a default encoder corrections proportional gain of 25 and a max correction rate of 60 RPM. So the error between the commanded and actual position will be multiplied by the gain to produce a correction of microsteps of up to 60 RPM. If I turn the shaft, you'll see that the encoder corrections are corrected based on the error proportional to the gain and also the max step rate. So there, it's a slow settle, but it does settle in. And if we're making a move, so I'm making a slower move with a little faster acceleration to introduce an error. So I'm tracking the following error in orange here. and we can see the error grows while we accelerate, and then the encoder correction gain will come in and settle that down towards 0. Even while we're moving, the correction to the following error will be added. And then at the end of the move, we get a 5 count settle, and that also is brought in with micro steps. So we're closing the position loop on the encoder in an open loop microstepping way using encoder corrections. So if we have an error on the encoder, we'll send microsteps to make the corrections. So that's the open loop microstep tuning and settling, and we can see we can run an open loop microstepper in a normal way.